Well, thank you very much. I appreciate it. I had this, I looked early on in the app and I saw like there was 5 people showing up. So last night I was having these cold sweats worrying that I could be speaking to only to my counterpart from Xilinx and maybe my mother or something would show up. But anyways, I do appreciate your time, and I have a small amount of time, so I'm gonna run through things pretty quickly here. But I believe that you will be getting access to the slides. And I have business cards, so if anybody has any questions or there's specific interest in having a discussion, just stop me and I can get you a card. So what I'm going to do here is give you a quick kind of intro. Who is Xilinx? Because I know that maybe some of you don't even know who Xilinx is or even how to say Xilinx. Some people call it Xilinx. So I'll give you a little bit of background there, kind of describe why Xilinx is here, what we have to offer, and kind of the problems that we believe we can help solve, and go a little bit across some of the common applications that we're seeing our devices used for, the benefits they bring to those applications, and kind of contrast that with how we differ from some of the existing solutions that are being deployed in other areas. Then I'll talk a little bit about what our strategy is in this space, and give you a little bit of background on kind of where we're going with this, and kind of, as you leave here, some final words and things that you might want to consider. So I've been I'm a semiconductor person, been in the industry for about 24 years. I work at Xilinx in San Jose, worked at Texas Instruments for a number of years in the multi-core DSP group, and worked on the Da Vinci product family, and I'm originally from Canada, so if I insert some A's in there, you'll understand why. Worked at a small company called Genum, we're the founders of SDI. Xilinx is a company that was the originators and creators of the FPGA Field Programmable Gate Array, founded in 1984. We just closed our fiscal year and came in at about 2.5 billion. We have approximately 3,800 employees rather. I wish it was all engineers, but it's not. We're sort of split. We've got a big group in Silicon Valley, in San Jose, and then we have various groups in Colorado and in Asia as well. So with that, why FPGAs for acceleration? Well, if you look at the industry overall, there's this massive growth in video. One of the things that I think is key is that in North America, we can kind of become kind of insulated. There is, everyone knows who Netflix is and Hulu and a number of the big brand names, but when you sort of travel around, and what you'll find is there are massive video applications, especially when you consider mobile and the whole social media. There's companies called YY or Kuaishou, and some of those are streaming, and the number of users could be 300, 400 million users that they have. And oftentimes they'll have 10, 15, or 20% of their users active at any one time. So you can start to understand that when you get 300 or 400 million users, that's a massive amount of volume. And obviously with bandwidth and mobile changing, I mean, the average bit rate in the US for wired is around 26 megabits. Now that's an average. Obviously there's certain areas with less. But that starts opening up, obviously, things like resolution, adding 10-bit HDR capability. So with that, you can see we've got this massive growth of video. It's going to become really the dominant traffic type. Simultaneously, we're, with many of the applications, sports, esports, gaming, higher frame rates are becoming critical. We're increasing the screen sizes. Screen sizes in smartphones were 4.5 now. Average screen sizes are moving up to 5.5. And so greater number of pixels. And that really is driving, from a network perspective, this need for greater compression efficiency. But when we look at what the the impact is on compute, it's massive. And when we look at things like AV1, and there's already VVC or the follow-on MPEG, we know that the compute is going to be even higher. And so when we kind of add all of these up, we're really looking at, from 264, almost a 21x compute overhead. And so people have been doing most of this in software to date. And so this is scaling 21x from a server perspective when you consider the challenges that we have with power, that renewable energy is becoming massively important for data centers and cloud. So how do we scale for traffic? How do we increase resolution? We need acceleration. That becomes the critical part, and that's where Xilinx and FPGAs become very interesting. Not only is all of that happening, but the world is more fragmented than it has been. More use cases are becoming a reality. And then we have this sort of disruptive nature that's going on where we're adding scalable for collaboration, and we're adding things like HEIF for image processing, moving from JPEG, because storage is kind of the other thing that oftentimes isn't discussed as much as bandwidth. That storage for all of this stuff becomes critical. If you look at Russia or China, in many cases their live streaming need to store at minimum all those live streams for 60 days. You look at where surveillance is going to be in the future. China has 160 million surveillance cameras. That's growing to at least 2x that over the next 4 to 5 years. And so having all of those cameras has this massive impact on storage. And then simultaneously, while we're rolling out all this infrastructure, we need to manage cost. Cost is critical. So this is why acceleration is needed. One of the things that we are seeing simultaneously is a lot of the streaming was kind of video on demand, file in and file out. Now we're seeing this massive influx of live streaming, and I think cell phones and social media impact is having a big effect on that. Obviously, with a mobile, and Apple is I think certainly helped in this area. Video collaboration, and video conferencing is a hugely growing application, and things like virtual desktop, et cetera. But all of these things have their small differences, but all of them have a time criticality, and that's why acceleration becomes critical. And this just kind of points out that if you look at X265 and run it, we did testing on kind of a Xeon E5 dual socket server. What you find is, to get really good compression, you trade off time, you trade off frame rate. But at the end of the day, with mobile, you really want to get that bit rate as low as you can. You look at drones, same sort of thing, where you've got a very tight channel, communication channel, and you need the bit rates low, but it's live. So this is kind of the challenge, and we have a good solution. I mentioned how, looking forward, there's this kind of fragmentation. In China, you've got AVS2. There are all types. JPEG JPEG 2000 is still around. We see a lot of fragmentation in the codec marketplace, and we don't think we're going to end up having a nice, simple life like we once had with 264. I think VP9 is going to be a critical one for some time. I think AV1, if you look at who the partners are, and I have a slide that kind of depicts that, but again, HEVC will also, when 264 has a long life ahead of it. So I looked at the Ericsson mobility report, and it essentially takes the world, breaks it down by regions, and gives you where they are with their mobile networks. What percentage of their population has available, say, LTE or 2G? And if you think about those networks, what the bandwidth capability is, in many areas in the world, especially when you consider like the Middle East, Africa, India, much of those regions are still at 2G and early 3G, which means streaming video over wireless is a really painful endeavor at the moment. But as you look forward in 2023, many of those regions are deploying LTE and have aggressive plans for 5G. So that means that there's this massive amount of the population that isn't even yet streaming video on their cell phone. And if you kind of think back 5 years ago, how many people were streaming video, and you didn't see the same amount. Now you go on a train, everybody's got their phone out. You're in an elevator, everybody's got their phone out. It's constantly that way. And so this is going to drive a huge amount of deployment. The other thing that's worth interesting is when you look at the world, all this green is the areas where Android is the dominant mobile OS. To date, Android doesn't support HEVC. So what does that mean? That means that 264 and most likely VP9 are going to be critical codecs from a streaming perspective for the mobile market. You hear a lot of people saying mobile first. Web pages were one of the first things that people had to think about, that mobile was a critical part of their strategy. If you look at India, India is today 86% Android based. And you think about moving forward as all of those people shift to streaming capability, that's going to be this massive influx requirement for VP9. I mentioned the importance for AV1. If you think about, you go onto the website and you see all these companies and you go, that's great, there's big companies there. But when you break those companies down in kind of their primary core markets and start thinking about, well, who drives the browser or the PC industry? It's all the key players. You think about smartphone. All smartphones are dominated by ARM. It's Android and Apple. Now, if Apple chooses to deploy AV1, that means one thing. If they choose not to, it means a whole other thing. And so this is, again, where flexibility and the ability to pivot and support codecs in another way. Apple migrating to HEVC and then deciding, hey, we're going to extend that to still images, has had this huge impact to the market. Now there's this fragmentation of, well, Android only supports WebP and JPEG. Apple supports HEVC and JPEG. So there's this, again, this fragmentation which requires flexibility and adaptability. Again, you see from a silicon perspective, us amongst many of our friends are all listed there. I think collectively, this is going to be a very extremely important codec, and one that we think will have a long-term roadmap to it. What I also did was kind of took many of those larger companies like Amazon or Microsoft. If you break them down to some of their sub-brands, let's call it, or sub-businesses, you can see that in collaboration, you've got Skype, you've got Link, you've got LinkedIn, WhatsApp, you've got Twitch, Xbox. These are just in themselves these massive businesses that really have a large impact. So I think when you kind of look at it this way, you can understand why AV1 is going to be a critical codec. Now, I think most people have understood, and many of the guys running their large data centers have felt some of this pain early on and talked to some of their original suppliers. And so they hardened solution. They went from CPU, software, programmable, flexible, you can tune it, you can iterate on it and continue to eke performance out over software releases. But then they said, wait a minute, this is too slow, too much power, too much cost per channel. So they went, okay, well, we'll run and harden the engine. Well, the challenge with that is that if you understand silicon, you understand that as we moved from 28 to 20 to 16 or 14 nanometer, and we migrate to 7 nanometer, the cost per square inch is going up like a hockey stick. And allocating square millimeters becomes a very risky endeavor. So you want a market where you understand it, you can forecast. The development time for devices at 7 nanometer it's very costly, but it's also a lengthy process. And so how do you call a market 3 or 4 years from now when that market is dynamic? And the average price for developing kind of at this range is at minimum $250 million. And then you think, well, what's a fair return on investment? A fair return on investment, maybe a 5x return. So now you're talking that you need a market that you can be successful in that's over $1 billion. How many markets can drive $1 billion in revenue? Well, there's PCs, there's cell phones. Well, that's why many of these hardened engines that you'll see are consumer focused. That means that they try to make trade-offs at the silicon level, and we see things like no B-frame support. Well, that's a critical tool for a codec. You'll see no adaptive quantization. These are all tools that, as an aggregate, help drive that bit rate down. We announced our next generation silicon, and over the last couple of years, we've already kind of hit $1 billion in investment. This is just a kind of reference point that shows that it's really important that you make the right architectural decisions. And so flexibility is we believe, critical looking forward. This is an example of, from the Moscow State University, they release generally this annual report where they take a number of HEVC encoders and they kind of map them out in their performance. And you can see that with the NVIDIA HEVC solution, because it doesn't have B-frames and a number of other tools, its ability to compress is actually worse than X264. So how do you move backwards in compression efficiency, yet you're supposed to be moving forward in the next generation codec? So this is just an example of how these trade-offs need to be made. From a Xilinx perspective, it's all about the right silicon, having the right IP with our partners, which we have at our booth. I hope you will come by and see us. But also, we're not delivering chips today. Now we're delivering boards and full solutions. And a lot of that happens with our partners. Johan, who will come up and talk later, is really going to dig into, when we talk about what we're accelerating, what particular areas that we target for acceleration, and how we're doing that, and building into industry standard frameworks. What I can show here is it's great to accelerate something, but as I pointed out earlier, it needs to be anchored at the right quality level. So getting the right bit rates at the right frame rate to support live. So what I'm showing here is a number of partners that we work with, and kind of versus the representative quality level, what we can achieve from an acceleration standpoint. Johan will go through is show how you can take an FPGA and essentially insert it into a sort of an industry standard framework like FFmpeg. We have many IPs or solutions that we've been working with our partners to address the overall. You need a library of functions. As I mentioned before, it's not you're just generally doing one thing. You need the ability to switch and be flexible and dynamic. And what we essentially can show is that we can run any or all of these. We can do still image. We could do 12-bit. We could do 12 bits per color. We could support MPEG-2 while we also support things like HEVC, because we are a totally programmable architecture. We do have, hopefully you've walked by and stopped by and see us. We have a number of demos here with many of our key partners, and we would certainly welcome you to come by and see the demos and really sort of have a deeper discussion about what it is that we're doing and how we might be able to help. The other thing to note is we have certainly kind of on-prem solutions that we can offer, but we're also being deployed in the cloud. And what I'm showing here is we are in AWS, we're in the Baidu cloud, Alibaba's cloud, Huawei, and Tencent. So we have the ability to run locally And also you can find those same devices in many public clouds, and we will continue to announce a number of those over the next few months. So with that, that was my fast run through. I appreciate your time and thank you. And if there's